4.2, we're going to look at expected values of discrete random variables. Also, we will look at variance and standard deviation as well. This idea of expected value is another way to express the idea of an average, and it's the average or the mean over the long term. So if we run an experiment over and over, and we record or observe the value of the associated random variable, at the end, if we take the average, that is what we would consider to be the expected value. So that's where that word expected comes from. It is what we would expect the average to be. Look at a simple example. Take an experiment of rolling a fair six-sided die, and we let x be the value that it lands on. So x takes on the values 1, 2, 3, 4, 5, and 6, commas. Okay, and those are equally likely to occur because we have a fair die. So to get the average we would expect over the long haul, well, we're just going to add up those values that the random variable can equal, and then divide by the total number of them, which is 6. And that's going to give us a value of 3.5. Okay, so the expected value for a roll of the die is 3.5. Now, 3.5 isn't actually a value that we can get when we roll the die, and that's going to be the case for expected value. It can be a value that that the random variable itself doesn't actually equal, all right, because it is an average, so it's not saying it has to be a specific value that it's equal. Okay, now, this way of calculating an expected value only works with equally likely outcomes. And that's not always the case, so we'll look at an example where our outcomes are not equally likely. Okay, let's use this PDF. This is the PDF that we generated for the experiment of flipping a coin 3 times, or we could also say we're flipping 3 coins at the same time, and we have our values of x and we have our values of their probabilities. All right, remember that is the PDF. Okay, we want to come up with the expected value of this random variable x. Now, we're not just going to take the average of 0, 1, 2, and 3 because they are not equally likely. So x values are not equally likely. So we have to take that into account. The ones that have a higher probability should have more say in what the expected value is. Or in other words, the values that have a higher probability should be given a greater weight. Okay, so the probabilities, I'm just going to say the P of x's are like weights applied to the x value. Okay, so to apply that, what we're going to do is we're going to take the x value and multiply it by its probability. Okay, so 0 times 1/8, that's just 0. 1 times 3/8 is 3/8. 2 times 3/8 is 6/8. And 3 times 3/8 is 3/8. Okay, so that gives us how much each of those values of x should contribute to that expected value or the mean. Now, if we look at the formula for the expected value, right, what we just did was this little piece right here, right? We took the x and times their probabilities. Okay, so then we've got the summation. That's this part. After we do the multiplication for all of them, we want to sum those up. So if we take that column and we sum those up, we get 12/8, and I didn't leave myself much room here. And 12/8 is 1.5. Okay, so our expected value number of tails when 3 coins are flipped many, many times is 1.5. Okay, here's another example, one that we've been working with. All right, so we want to calculate the expected value, all right, which is a mean. All right, so we're going to first multiply the x values times their probabilities. We take x times p of x. So 10 times 0.2, we get 2. 11 times 0.3, we get 3.3. 12 times 0.2, 2.4. 13 times 0.1, we get 1.3. 14 times 0.2, we get 2.8. All right, so we now want to do the summation part. Summing those up, we get 11.8. Okay, if you want more practice of finding expected value, you can go back to the examples that we looked at in 4.1 and find those expected values. Okay, now let's look at variance and standard deviation of a discrete random variable. So we're still with these measures, coming up with a measure of variability, and standard deviation is going to give us the average distance away a random variable value is from its mean or its expected value. So we have the formula for variance is given there as sigma squared, and we see that we've got x minus mu, so individual values of x minus the mean. All right, so there's the difference or the deviation, and then we square it so that when we add them up they don't become 0. And now to add that weighting for the probability, we multiply that squared difference by the probability, okay, and then we add them up. So it might be good to put parentheses around all this stuff to say that first we do all of that for each value of x that our random variable takes on, and then we add it up. Okay, and that gives us the variance. To find the standard deviation, we take the square root. All right, we want to find the variance and standard deviation for our previous examples. So let's look at the example where x values are 10, 11, 12, 13, and 14. And then we'll look at the one where we had the gadgets as well from 4.1. All right, so I'm just going to list out our PDF again. So our values 10, 11, 12, 13, and 14, and our probabilities 0.2, 0.3, 0.2, 0.1, and 0.2. Okay, so we want to create a column where we take those x values, we subtract the mean, square it, and then multiply times the probability. All right, so if we start off with x equal to 10, all right, we're going to take 10 minus the mean, which we calculated to be 11.8. We're going to square that and then multiply it by its associated probability of 0.2. Okay, that gives us a value of 0.648. Okay, make a little bit better 8 there. All right, let's look at the next one. So now our x value is 11. All right, we subtract the mean, 11.8. All right, we're going to square that difference, multiply by its associated probability of 0.3. And that's going to give us a value of 0.192. All right, now we go to the next value of x, 12, minus the mean, 11.8, square that. All right, times the associated probability of 0.2, and that's going to give us 0.008. Now we take 13, subtract the mean, square it, times the probability of 0.1. That gives us 0.144. And now we take 14, subtract the mean, square it, multiply by its probability of 0.2. We get 0.968. Okay, so we went through and we took the difference, squared it, multiplied it by its probability for all the values of x for this random variable. So the variance will be the sum of those values. All right, so if we add all those up, we get 1.96. Okay, so that gives us the variance, and standard deviation is the square root of that. So the square root of 1.96, we get 1.4. Okay, now remember standard deviation just gives us an average distance away from the mean. So yeah, what we just discovered then is that the average distance away from the mean of those random variable values is 1.4. All right, so let's look at another example. We're going to kind of start from scratch here, where we're first going to create the PDF table and then use that to find the expected value. Okay, so a friend offers you the following deal. For a $10 fee, you may pick an envelope from a box with 100 seemingly identical envelopes. However, each envelope contains a coupon for a free gift. 10 are a free gift worth $6, 80 are worth $8, 6 are worth $12, 4 are worth $40. So based on the financial gain or loss over the long run, should you play the game? Okay, so what this is asking is, what is the expected value? Like, on average, if this game was played over and over again, would you expect the winnings or the losses to be? Okay, so it doesn't ask for this exactly, but this is what it's asking for. What is the expected value? Okay, first thing we got to do is create the PDF table. Okay, so for a PDF table, right, we want a column for X and a column for the probability. And we'll start off with those. Okay, let's fill in the values that X can take on. So X is going to be our winnings or our losses. So if we take the first scenario where there's a free gift of $6, we would get $6, but we had to pay 10 to play. So our net is a loss of $4. So X would be a -4. And in the second scenario, all right, our gift is worth $8, but we paid 10. So that's a -2. Third scenario, we get 12 minus 10, so that's a net of +2, or winning of $2. And then the last scenario is 40 minus 10, so we get a net of 30. Now let's run through the probabilities for each of them. Okay, so there's 100 of envelopes, and 10 of them have that $6 gift. So that means that 10 of 100, or 10%, probability of selecting one of those. And for the $8 prize, there's 80 of those, so 80 over 100, or 80%, or 0.8. And $12, there's 6 of, so 6 over 100. So 6%, or 0.06 in decimal form. And of the $40 ones, there's 4. So we got 4 over 100. 4%, or 0.04. Okay, to find that expected value, we need to weight each of those values of X by its probability, so we multiply those. Right, so -4 times 0.1, we get -0.04. And then we get -2 times 0.8. That gives us -1.6. All right, then we've got 2 times 0.06. All right, so we get 0.12, and then 30 times 0.04, and that gives us 1.2. Okay, so expected value, right, or we can represent that with mu because it's a mean, right, is going to be the sum of those values. So just a reminder, the sum of X times P of X. All right, so adding that column up, we end up with -0.32. All right, so if we played this game over and over and over again, we would expect that over time, the average of the winnings and losses would be a negative 32 cents. Okay, here's another one. A physics professor wants to know what percent of physics majors will spend the next several years doing postgraduate research. He has the following probability distribution. So we're assuming that the random variable is counting the number of students that do postgraduate work. So number of students doing post-grad research. Okay, so X can be 1 student, 2 students, 3, 4, 5, or 6 students. And we're given all the probabilities except for the one that goes with 4. And so we need to first of all find that probability that X is equal to 4. All right, well, we know the total probability should be 1, so we want to subtract all of the other probabilities. So if we add all those other probabilities up, it sums to 0.85. So 1 minus 0.85, we get 0.15. So that missing probability is 0.15. Okay. All right, next question. Find the probability that a physics major will do postgraduate research for at most 3 years. So one way we can write this is that the probability that X is, now it says at most, so that means the largest value is 3, so it can equal 3, or it could be less than 3. So we want to know the probability that X is less than or equal to 3. So we just look at the probability, look at the values of X that satisfy less than or equal to 3, and that's going to be 1, 2, and 3, so we add those probabilities together. 0.35 plus 0.2 plus 0.15. And we get 0.7. All right, on average, how many years would you expect a physics major to spend doing postgraduate research? All right, let's go back and use the table to help us do this. So again, it's asking about expected value. So we want to weight each of those values of X by its probability. So 1 times 0.35, we get 0.35. 2 times 0.2, you get 0.4. 3 times 0.15, we get 0.45. 4 times 0.15, we get 0.6. 5 times 0.1, we get 0.5. And 6 times 0.05, we get 0.3. Okay, so then our expected value is going to be the sum of those values. So again, that's a mean value. And we're taking the sum of the x's times their probability. And adding up that column, we get 2.6. And that is the same units or label as the x value, so that is students. So we can expect over a number of years, taking the average, we would get 2.6 students going on to do postgraduate research.